relevant to today's lesson, because today's lesson, guys, the basis of today's lesson is this one is to understand the DC motor. Next lesson we're going to look at a little bit to do with galvanometers and loudspeakers, and then we're going to start looking at main ID 2, which is electromagnetic induction, and you'll understand what that means in a moment. Right.
I have a quick question about it. It's probably got nothing to do with it.
Yep.
Why do they have such a big magnet, or how does that affect it so much?
That's what we're doing this afternoon, so I'll talk about that. Okay, so motor effects says very simply that you have a conductor or a wire in a field, or a magnetic field. While there's a current flowing through it, it will experience a force, right? Yes? Yes, we did. I actually gave you a whole lot of homework on that too. All right, so what you simply had was you had a wire, and let's make it very, very simple in this case. You had a square, well, you made it a circle, but say it was a square, right? And then it went out that side. And across that, you have a magnetic field. And I can arbitrarily say on this diagram which way the current flows in it, can't I? So let's say the current, in this case, is flowing down that one. So that's I is down on the left-hand side, and it's up on the right-hand side. So when you measure the force, yep, using the F, B, and I, the B will be that way, won't it? Sorry, F, B, I. So on this side, watching, if you use your 3 fingers or your push rule, whichever one you like, the B is across, the I is down. So this on the left-hand side. On the left-hand side, this wire will want to be coming out of the page, and the right-hand side, it will be want to go into the page. Because it's on a spindle, it will then start to turn that way, which if we're looking end on from the bottom, would make it turn clockwise. The problem is, if I continue that current that way, when it flicks over, now what happens is that the force on the right-hand side is up. Riley, really important that you're focusing on this. So at the moment, this one has a force out of the page, out of page. This one has a force into page. Now, when they swap over, they'll want to reverse direction, won't they?
I thought that as soon as it's perpendicular to it, the force starts going the other way.
No, it doesn't. So when it flicks over, if the currents were still the same way around, it would mean that they would want to turn back. Now, the way we avoided that was if I label that A and I look at the wire end on, what we did was in half of it, we took the insulation off, and the other half we left the insulation on. So in this position where the current flowing, when it flicked over, there was no current flowing because the insulation was still there. So the momentum carried it round, and then it comes back on. And what you end up with was this really rough rotor going click, click, click. It wasn't running smoothly because it was only having a force acting for half of its motion. Yeah.
If you shave off all of it, then you'll flip one way, flip the other way, and then eventually get.
It'll eventually end up like that. Exactly, and it will. Then you'll have a short. Then it will weld itself to the contacts, and it will melt, and then you have a mess.
Yeah.
When say this is the say this is the direction of the force curve.
Yep.
And this is the coil as it's turning. Does it stay directly upwards, or does it go 90? So would it stay as it's turning? It stay like that, right? So if this is the direction of the force directly upwards.
Okay. Now.
No, it doesn't.
No. That's a point that I want to bring up. I want to graph some stuff with you, and it's another point. But the first point was that motor, it was only on for half of its turn. Then it switched off, and its inertia carried it round, switched on again, got another kick, switched off. Now, you don't want that in a motor. So when we design motors, DC motors, we need a way of keeping electricity running through it constantly, and we need a way to make sure that once the current always flows the same way on the same side of the motor. And there's a trick to that which I'll show you. No. I'll show you how it is done in a moment. First we'll answer the other question.
But just what I'm trying to say is, say like you stop its rotation when it's at 45 degrees to...
I'm about to answer that. So, again, magnet, field, magnetic field across. And I'm going to do this end on as well. So you can imagine now there's an axle, right? And there's a coil that looks something like that, right? That's really badly drawn. And the magnet is here and here. Right, and in this case, you have a coil looks like this, right? So that is that there. What angle is this wire to that field? 9 degrees. Now, as that wire goes up 3/4 way turn, so it's now at 45 degrees, what angle is that wire to the field? 90 degrees. What angle is it there? What angle is it there? So, as long as I keep the current in the right direction, what is the force on that wire all the way around? It's always at 9 degrees, so the force will be the same.
So, how does it stay 90 degrees so as it turns? Because it's a...
Okay, I'll try and explain it this way. If
Oh, wait, no,
magnetic field.
hang on, I can only go one question at a time. Imagine, if you like, that that box there is a magnet, and the magnetic field's coming across the desk from right to left, and there's the coil. That wire's experiencing force on the wire parallel to the magnet, and the same on the other side. As it turns, it always stays at 90 degrees to the magnetic field, doesn't it? I have to go that way, but your motor won't work that way. Where in that term is there going to be a change in the force? It's always at 90 degrees to the field, so that term's always 1. The force on it is always going to be the magnetic field strength times the current flowing through it times the length of the wire. Does the magnetic field strength change? It does a little bit depending on your design your motor, but it's essentially the same. You have a big motor.
So I read somewhere that they don't think that this physics course that we do is recognised at uni. Like apparently the first thing they say to at uni if you do a physics is, oh, we want you to have some understanding of maths, but we expect that none of you have an understanding at all of physics.
They say that in any science course. When I went back to uni, we spent the first 4 weeks we redid the HSC.
Yeah, but they think that because like they don't think we're smart enough for actual calculus, like because the projectile motion we use is 400 years old. We can't do actual physics questions, that sort of thing.
Yeah, just don't worry about worry about what you have to learn to get through the HSC to open the door to get there. Then worry about learning the other stuff. Okay, now, yes. No. No, ours has been in our drawer forever. Now, next thing. So the force on the wire, as long as you keep the current in the same direction through all its motion, is going to be the same. Does that mean the torque is going to be the same? No. No, not at all. And in fact, if you look at the torque, if you go through theta that way and torque this way, when the coil, so let's draw a explanatory diagram. There's 2 magnets. The magnetic field again goes that way. If I draw it that way, which side is the north on this? South. I'll draw my coil into it. I'll do it green this time because I can. Not for any special reason, I can. Okay, at that angle, like that, what angle is the coil to the field there? Is that 90? Is that the coil at 90? Or is that the coil at 90?
Sarah, are you looking from top in that?
Where is the maximum area of the coil exposed to the field? Is it when it's flat like that or like that?
Oh, when it's like that.
Right. Okay. So at the moment the angle is 0. Yeah.
Oh, because it's
It's flat to the field. There's no area.
whereas
So at that angle, it's got 0 torque. As it spins through, it'll go up to maximum torque, go down. Then what happens?
is that like a sine curve?
No, because it does this. So that's 0, 180. No, sorry, not 90. 90, 180, 270. So, guys, really, really, really important for you, and this is something that Steve Fogwell was explaining on the, you have a formula, F equals BIL sine theta, and you have the angle, torque equals, you need to know which theta and how to read that theta that you're talking about. So you need to know that for this one, that theta is always 90 degrees to the field, but you need to know in the motor in that case, as the rotor turns round, or the coil turns round, that theta will be changing. So in this case, either of those wires are experiencing always a force at 90 degrees to the magnetic field, but this thing here, it talks about the whole shape of the coil and its orientation of the field, so it does change as it goes around. Does it make sense? It's important that you get that.
So do you ever have this question where like that coil will be offset so it's not 90 degrees?
Yes.
Really?
They asked the question at Steve Fogwell showed, you saw it, where they asked you the force in the wire for something which is orientated at 35, I think it was, to the field. And guys, just be aware of that. They had a question in the HSC where if this was the coil, it was at an angle like that, and the field was going across, and they asked you to calculate the force on that wire there, and they asked you to calculate the, not 0, they asked you to calculate the torque on the coil. And what you had to realise was that the theta for that wire was 90 degrees, but the theta for the torque was...
So then like with because like we had the magnet 90 degrees, and if we progressively moved it around, it would get to the point where it would stop, it would slow down.
Yep, that's right.
Yeah.
Okay.
These are still sine curves.
So have you guys clear on that stuff?
That's okay.
It's important. Right.
That one was just, yeah.
Okay, let's do the stuff we have to do here quickly. Now,
It's code in it's wrong. That one, is that what you're saying? No, it's math.
It's got like all the money.
What, like the background?
all right, listening in, please. This is going to be relatively quick, relatively... Pardon? So, guys, this part of the course is just simply learning labels. You've just got to, you're supposed to know the parts of a DC motor and what they do. And you're supposed to do the same thing with AC. The good thing about AC and DC motors is that the parts are essentially identical until you come to talk about induction motors, except for one piece in it. So once I teach you a DC motor, it's very easy to do AC motor. When you look at the things you need to change the DC motor to make it work better, it's exactly the same for the AC motor. They're just the same thing. Now, the other part of it, you're also supposed to learn about generators. Now, what do I need to make an electric motor work?
Electricity.
Electricity. I put electricity in, you get a motor effect, and it causes the wires or the coil to spin, and you get kinetic energy out of it, right?
Yes.
To make a generator,
It's opposite.
it's just the opposite. I put kinetic energy in, and I get electricity out.
That's why.
And one of the things I will show you this afternoon is if I get an electric motor and run it as a motor, I can then just reverse it round and I can actually get a current out of it.
Does that mean that if you, so you get a motor which produces kinetic energy, which feeds into the electric generator, which produces electricity, which feeds the motor, and then
But it
you
will
have an infinite loop?
No, you won't because of resistance. It's a good thought.
I can have a bicycle in space.
Now, so the good thing is that for, once you've learned a DC motor, you've essentially learned AC motor except for one small change, and you've learned generators. So all this stuff you're supposed to do, where they say learn the parts of a generator, when you do DC motor, you've done it. When they say learn the parts of an AC motor, you've done it.
How does the AC?
I'll show you, we'll share the difference.
So because E equals F times D according to that, does that mean that the torque is equal to work? Work is equal to
In case you feel like a dog in a chain.
Kind of, yes. Yes, I know it's there. Now, this tangle a bit. The other thing is, and guys, shh. The other thing about this is that this is the lowest level of learning possible. It is not conceptual. It doesn't require formulas or anything. You just got to know labels of names of parts. You just got to know what they do. It's straight memory work. Now, as Steve Fogler did say on Friday, he said if you look at something, you'll eventually forget it if you look at it once. If you look at it twice, you might remember a bit longer. The way you remember things is essentially re-accessing them over and over and over until they stick in your mind. Like the reason that you can quote your favourite TV show is because you watch it 25 times or whatever. What I have on the board behind me now, very few people have eidetic memories where they watch a show once and they remember the script. There was one famous musician.
Mozart could do that with music.
Mozart did with the music. In fact, famously he did it where there was a famous piece of sacred music where the score was locked away and no one was allowed to see it except the musicians. And there's only one copy, and he went and listened to it and then walked out and then wrote out the score from memory. Note perfect. It was a half-hour piece, I think, something like that. Okay, focus on this. What I have behind me is a simple DC motor. So you have a coil with a current that runs through it between some magnets. Okay? Now there are some things missing from this which help. First thing, the coil is going to rotate. It's going to spin, right? For it to spin, it has to be attached to some sort of device which will let it spin. You find those on bikes. This is called making connections. No, what lets wheels spin? Starts with A. Axle. So through the middle of this coil is going to be an axle. The axle is going to rest on some bearings. That's practical, so it can spin around, right? Because that thing's, but for a motor, you won't necessarily only have one coil. You could have lots of coils. So the whole device in the middle which spins, that's one coil, but say I put a second coil on it that went at 90 degrees to the first coil, so I have two coils. In fact, most DC motors actually have 3 or more coils for various reasons. So, alternator, it's a DC generator, yeah. So with this, the thing that spins in the middle, which has the coils on it, is called the rotor. That middle bit's the rotor. Also, it has got another name, which is commonly around, and is in the course. It's called the armature. So the coil is just the wire, one loop of wire, The bit that spins in the middle is either the rotor or the armature. And it's labelled there as armature, you can see it. On the outside you have some magnets. Now, the motor doesn't care where your magnetic field comes from. It doesn't care whether it's a permanent magnet, like it's drawn on the board, or whether they're electrode magnets, which turn on when you have some loops of wire and you put, well, you've seen electrode magnets, you know what they are. We use one in the class when we're doing the Galileo thing. So it doesn't, the motor doesn't care where the magnetic field comes from, it just needs a magnetic field. But they don't move, and because they don't move, they're called stators. Or stationary, or whatever. But they don't move because they're called stators. You need to get electricity into this thing somehow. And what they commonly have here is and I'll draw it, is they commonly have a housing, which is just a simple piece of metal. It normally has a spring in it. And then at the end, you'll have a block of carbon or graphite. And that rests against the side of the axle, against the commutator, which I'll talk about in a minute. And you have an electrical supply to that. And so the electricity flows through that into the coil. That is called the brush. The brushes are the parts that wear most easily on there. Yep. What happens with them? They slowly wear down, and that's why you have a spring. It keeps pushing them further out. Ah. AC brushless motors. We'll talk about those. Because I'm not doing the course, I've never looked them up, to be honest. Now.
I thought you did say brushes, not brushes.
Yes. So the brush is the device which allows electricity to flow into the coil. And then you have this thing called a split ring commutator. Now in the HS split, I'll explain that in a second. I'll actually show you. The thing is, in the HSC, for some reason, they have this fixation that says the way you identify a DC motor is you look for the split ring commutator on it. If you see a split ring commutator, you know you've got a DC motor. And there's actually big questions in the HSC. Is this a DC motor? How would you identify it? And you say, it has got a split ring commutator, it's a DC motor.
Is that the thing?
That's that ring thing there. Now, in an AC motor of this sort, you don't have a split ring like that. You have two rings, and you actually will see two rings with the brushes in different places. And I'll explain why later. But as I put this on a forum one day and asked about a question to do with this, one of the physicists on there said, why on earth would you even ask that question? I don't look at the motor to see what it is. I pull out the box. Or I see if it says DC stamped on it. You know, it sort of said, that's a stupid question. In real life, no one ever looks at the commutator to see if it's DC or not. And he's quite right. But the HSC has a fixation. HSC has got a fixation about that split ring commutator. So guys, if you've got a question about identifying a DC motor, the answer is the split ring commutator. Why is that going so stupid on me? Okay, guys. I really want to go through this bit because this is the important part before I give you some notes. Okay, in this, what you see here is a very, very simple model of a motor. Okay? Now, a model is just simply something which represents something in real life, and we use them for a variety of reasons in physics. One is because some things are too fast to see, some are too slow, some are too large, some are too small, and some are too complex. So this is generally to do with complexity. If I just, at the moment, Marnie, how much current is flowing through that coil? Zero. There's the bushes, there's the voltage, so you've got two bushes, and you see the split ring there, the thing that supplies the current to the coil. The brushes at the moment are in the split, in the gap, so there's no current flowing, is there? No. I'm just going to step it forward one. Now, the negative side of the supply is connected to the right-hand side of the coil, so the electrons will flow around this way. So it goes basically in an anti-clockwise direction. The current then is clockwise.
Hey, sir.
Yep.
With that motor when it was 9 degrees, like, because there was no current acting on it, does that mean if you tapped it one way, it would go that way? If you tapped it the other way, it would
No.
right, so
No, and I'll tell you why. In the sort of motor you made, yes, but not in this one. In this current position, the left-hand side of the coil is positive. The right-hand side of the coil is negative, correct? So, Marnie, you can tell me which way is the force acting on this left-hand wire? It's the hand thing. So B, in this case, is from the bottom of the board to the top, right? I, try and work it out, give me an answer.
Wait, which way is what? That one. Which way is I going?
But B is going to be up the board. I, well, which end's the positive end? That's positive, so that's the current is that way.
The force coming out of the paper.
Don't forget the orientation of the it's going down. Let's see what you get as I step it forward one.
It's going in a direction.
So watch what it does. Yes, that's what they do. Now, you notice the force is downwards on that side and upwards on the other side, correct? Okay, so I'll step it again, and I'll keep stepping. Now I'll get to this point, and what's happening to the current? Basically isn't any. Now remember, this wire here, at the bottom of the little diagram there, was the one that was on the positive side of the supply, wasn't it?
Yeah.
Now when I go one more step round, 0, that wire now is on the right-hand side. What is its?
The opposite.
It's now become a minus,
Yeah.
hasn't it? This one is now
Positive.
positive. It used to be negative, but it's become positive. So what the split ring commutator has done is ensured that the current always flows in the same direction around the coil, so the force stays the same way. Otherwise, what would happen is what Brad said before, it would end up just sitting there like this, your motor would burn out. So the role of the split ring commutator is to make sure the current stays the same direction in the coil. Okay? Let's go through this quickly again. Axle allows the motor to spin. Coil, what does the coil do?
Transfers current.
Carries the current. What does the armature do?
It's an rotor.
Or the rotor, it holds the coils. And it spins, you're right, it provides What does the stator do?
It stays the same. It stays still.
What does it provide? Provides the magnetic field for the motor to make it work, because you need a motor effect. And the big idea in this is that forces on a current in the magnetic field can be used for devices. One of them things. What do brushes do, Riley? They conduct the transfer electricity in the coil. What does the split ring commutator do?
Tell you if it's direct DC or AC.
It does, but what's its real job? It's to make sure the current flows in the same direction in the coil all the time.
Woo! Split ring commutator is really similar to a distributor on a.
In a very no. Well, what the distributor does is it fires off the spark plugs in turn.
But that's pretty much.
You could use it for it, but no. Does in a way.
It's just the distributor.
Now, obviously, if you want to have obviously with the limits, you want to make your motor go a certain speed and certain force, right? You increase the current, increase the magnetic field, but if you only have one coil in a motor, it's going to be very jumpy and jerky, isn't it? It's just going to go flick, flick, flick. You're going to get very uneven torque curve. How could you improve the torque curve on this thing? Yep.
On the split ring commutator on that one, what the brushes, is that somehow attaching an
They're not fixed. They're supposed to slide past.
Okay, so it's not attached.
Not attached. No, it's just a bad diagram. If I wanted to want to improve the output of this and make it smoother, I could add another coil, right? So what I could do is I could now have a coil which goes at 90 degrees like that. And so it gets a double push along, right? But what does that mean I have to do with the split ring commutator? Have to make into quarters so that I have opposite feeds one coil, opposite on the split ring feeds the other coil. So if you have 3 coils, which is very common, you'll have 6. No. Actually, you can have, but you don't typically in a simple motor.
So you got the coil. I put like coils. So you know the wire.
Yep.
And you made it each coil would just be a coil apart, so you get a whole entire circle of wires, if you know what I mean. Like you can imagine it being just like a circle with dots, if you look at the front
Yep.
view.
Yep.
And then you made it split ring commutator, each like would split up all those different wires.
Yeah.
You would essentially get an extremely screwed motor.
Yes.
It's like a whole, ordering it. To make it two different.
So what you have there is actually the inside of a very simple motor. And you can see the split ring commutator, you can see the axle, you can see the armature or the rotor, you can see the coils, and you can see the laminated iron bands which are used to increase the magnetic field there.
How does that make it car work? So is that what the battery does? Is that the battery turns that thing on and then that turns and that somehow
Electric cars.
So, thanks guys. What we're going to do